Well, I have to say that I'm really excited to have this opportunity to share what we have been doing at Google DeepMind recently. Most of the things that I will present are published, so there are other things we're doing. We tend to publish everything we're doing, but of course we try to publish and present at public talks like this one, only the things that have been published already. But I have to say it's relatively updated, and I will hint on a few things. Clicker might not work. Let's see. Oh yeah, there it works. That's a little bit of the outline of the presentation, but let's go directly into the first part, which is just an introduction of my company. Well, Google DeepMind was founded in 2014, and actually joined Google in 2014, but in 2010 it was founded as a small spin-off of UCL. And then was joined with Google Brain, which is the AI division for Google, created in 2011, and then we joined forces in 2023. So it's a relatively recent merge that we actually went through. And I think that the scale at which we are operating now by joining robotics and AI in the context of machine learning has been quite major, and we are now a group of more or less 200 people working in robotics and AI. The idea of what we are trying to do is actually to solve artificial general intelligence. And I just wanted to bring up this slide because the generality is an important part of what I will present today. We know that for a certain number of tasks nowadays, we can automate through robotics the task itself. And this is very clear if you look at the cost of your iPhone, the cost of your car. And the reason why the cost is so low and it becomes consumer electronics, consumer hardware, is because we can automate the assembly process. But of course, it's not very flexible. Your iPhone is identical to the person you have on your right-hand side, and the cell phone more or less is the same. So it's very difficult to automate a general assembly if you want. That's why robotics in particular, and the things that we'll present today, it's all about generality and how can we make robots more general in the way we program them to do things for us. And that's important to keep in mind. That's another important slide that I always bring up. How do we make this tool that we're working with at Google DeepMind general enough to address the different things that we can do? That's an important part of what I need to present, so pay attention to this one at least. We try to abstract away from problems and from the specificity of problems by having a representation that can fit multiple problems. That's what it is. And the way we do this is by representing and using a representation that is very common in the machine learning community, and in particular in the reinforcement learning community, where you assume that you are developing what we call an agent. In control theory, I'm a control theorist by background, so in control theory will be a controller with state estimation and also the control part of the intelligent part. So it's the agent. The agent receives certain information from the environment and certain information that defines what task the controller has to do. And the agent can do actions in the environment. And as you can see from this slide, the environment can be whatever you think of. It could be a computer, for example, where you send clicks and you provide a few pointers position. And the actions, the observations that you get could be just a video that you're receiving. But if you are a robot, then it becomes more complicated. You have like a lot of possible actions. You can apply forces. You can apply movements, displacements. You get observations of different kind, like tactile sensing, cameras, and so on. And you can think of the problems you're working with every day, and you realize that this could be a good way to represent a sort of meta representation of what you're trying to do, especially if you are trying to develop a controller or an agent that works on a computer. So that works really well. A bit that is often underestimated in this picture is this, what I call task specification. How do I specify what I want this agent to do? Usually it's coded inside the agent, and we don't really put it there. It's not explicit. But in this slide, it has to be explicit. Because what we are trying to do at Google DeepMind is to be as general as possible in the way of describing what I want the robot to do for me, what I want the chatbot to do for me. And it has to be very natural. Initially, it was a reward signal that in control theory, optimal control theory is the cost function. But more in general now, we're looking at things, and I will present a few things initially, where it's all about text, images, and for robotics, of course, it's like the natural way we teach each other to do things, through language, through images, and maybe through kinesthetic teaching, by doing what I want you to do, right? So we are moving away from an engineer that codes a reward function or an optimal control function or decides what has to do into the area where you want to just say the thing. You want to write it down. And it's a big change, and that's, again, connected with the generality. So let's keep that in mind. Big novelty, I don't think I need to describe this to you. Deep neural network are a way to describe these agents, and they're becoming extremely powerful in these days. I will say a few things about it. This is an old slide, so I don't think I need to go through it too much, but I want to stress on one bit. Language models are extremely very powerful in these days. You can play with them. You have Gemini, you have ChatGPT. Of course, I say Gemini because that's a Google one first. What I really care about in this slide is that somehow these language models understand the physics of the environment. That's an interesting one. Who have thought that this could be a possibility? Honestly, when I joined back when I met Giacomo, I was in the IIT, the Italian Institute of Technology, and language was all about, oh, there's no language without touching things, moving things, because language is grounded on our actions. Yeah, sure enough, but chatbots somehow can steal that knowledge from us by parroting what we're doing, generalizing over it, and they can make a sense of the physical environment and of the objects we are surrounded by. So that's kind of interesting. The bottom right box is the one that I'm basically hinting to. They know about affordances. They know what you can do with a potato, what you can do with a laptop, what you can do with a cookie, though. It's sort of already hinting on where I'm going, right? Language models can be used for robotics because they know about things. They know how to decompose actions into sub-steps, which is a purely robotics expertise, but was already coded in the language that these chatbots had the chance to see before being used. This is more to say that the tool is extremely powerful. Image generation, I know how many of you have seen or played with this kind of tools that are nowadays available online. So the one that Google released was blocked because it was unfair to sort of diversity in the communities. But there's plenty more running online. You can give it a try yourself. They might not be as accurate as this one because this is very, very pristine in the way of creating images. But what I'm trying to say with this slide is that there are image generation tools that are based on the ideas that I just described, that from the text at the bottom of this image, create the image on the top. And you see that the accuracy, but also the level of details and the level of modeling of the generative process without knowing anything about light, reflection, surfaces, and many other things that we thought were fundamental to understand how to generate images, can indeed generate all of these. Like top left is the one famous one because it's a transparent duck in front of a painting, and you see the reflections, you see the surface, you see many things that you can do with a rendering engine. But the fact that you can code everything without any law of physics from images, it's quite remarkable. This is the one that I added today, just because, again, I think it's an important one for robotics. This is Genie, is a relatively recent tool, this is a relatively recent neural network that we released. When we didn't release it, we published the paper. This is a neural network that can generate video games from images. So, of course, it has been trained on video games that look a lot like Super Mario, so no big deal. What is interesting, though, it's a relatively small-scale project. So imagine how to scale this up to a more complex environment. Small project in the sense of the amount of compute that was used to train this kind of neural network. But the video game on the bottom is actually a video game, as in order to get that video, you need to play with it. You need to have send actions, like in keyboard actions, to the video game. And it's created from the prompt, so from the images on top, which are synthetic images on the left, real images at the center, and sketches from kids on the right. From the image, you create a video game that you can play. What is relevant on this slide, and that's what I want to stress, is that you see the law of physics in there. You see that a character can, climb a ladder, can jump on a surface, and all of these make sense to us, clearly, but it's interesting to see that the deep neural network can also grasp the law of physics, the law of interactions, and can generate videos from actions, which again, for robotics, you can imagine is a big deal, because you can take one of these approaches and imagine, given the current view of the robot, you can imagine what could be the result of taking a particular action. What would be the reaction of me jumping off this stage, right? And it's giving us predictive capabilities that we know, for what we know about the human brain, are fundamental to act in the environment, the ability to predict what will happen, have a physics understanding of the environment. I'll be fast. I'll keep an eye on the time. So yeah, I'm running late on time, so I'll speed up. Why is this possible? Well, I have to say, I need to acknowledge a couple of things. One is our understanding of the human brain and how to bring this knowledge into the neural networks that we're using. Things like convolutional neural networks, which are inspired to the V1, visual cortex. Things like attention systems, coded in a very general way, in a very parametric way, is a fundamental ingredient to understand how information processing can be implemented into an artificial representation of the neural network itself. The other big important component, I need to be fast on this one, is that the computing scale is really increasing in an unprecedented way. I need to make this example because I think it's very powerful. Any technology we live with today, if we think that in 2 years it will be 10 times better, we will be really surprised. Take a car, if I say in 10 years it will be 10 times more power efficient, then you'll be like, no way, it's impossible. 10 times is already kind of a big deal for any technology we're surrounded by. Well, in this slide you see that a compute in the last 30 years, well, this is just in the last 5 years as a matter of fact, but increased by 10 to the power of 15. So it's a blowing number that I can't even myself make sense of. But computing is becoming a very cheap technology, but also getting close in terms of the size of the memory and the representation that we have. And it's at the bottom of this slide. It's very close to the human brain. Let's face it, like it's really the case. The number of connections we can realize nowadays on a relatively small NVIDIA GPU, it's comparable to the one of the human brain. So let's face that technology is getting really close, and it will be possibly better in the future. So that's always to keep in mind. Oop. Let's dive into robotics. How am I doing with time? Okay. Well, I present today GDM Robotics today, so Google DeepMind Robotics. We have a bunch of investments, mostly in dexterity and agility. We work with models and algorithms, the one I just described, so representation of the neural network. We work with simulations. We have a tool that you can use It's called Mujoko, is a tool for robotics, is open sourced, so you can really be part of the open source community, but the core of the developers of this tool is at Google DeepMind. They're good friends of mine. If you have any trouble with bugs, something that doesn't work, reach out to me. As Giacomo was mentioning before, since he visited my lab recently, we do have a quite scalable, that's the term we use, but it's quite massive lab full of robot arms, doing many things, but mostly collecting data. As you can imagine, that's an easy one. These approaches are very data hungry, but also evaluating continuously what we are trying to do. So it's not just data generation per se, but it's also a big component of, if I have this neural network, is it really doing what I'm supposed to do? Yes, we use a lot of simulation, we use a lot of other things, but the proof that what the robot has learned is the right one requires evaluations and tests. So it's basically a bunch of robot arms, industrial arms, playing with toys in front of them to check whether or not they learned the task they were supposed to learn. A few things that we have worked on recently. I just skimmed through a few papers. As I said, simulation is an important part of what we're doing. Data is difficult to get from real robots, so an easy way to do and to go about it is to learn from simulation and transferring on the real world. And I think, I don't want to enter too much in the details because actually the next video is a bit more interesting. But we can solve tasks as complex as the one you see here. The humanoid that you see in this picture, the black small humanoid, is tasked with a couple of things. On the left needs to navigate in the environment, avoid the obstacles, and go to different locations in the area. And on the task on the right, the humanoid has to push the basketball ball into the green box. What is interesting about this paper is that the agent just sees images and from the camera, from the first-person camera, and just controls the joints of the robot, the movement of the joints, and produces everything else it will see. So in order to do this, the robot is estimating its position in the environment, the presence or non-presence of obstacles, and then it needs to plan for footsteps in order to avoid the obstacles and get to the target. Or, in the right-hand side, even estimate the position of a moving object in the environment, in this case, the ball. I don't know if you have a video. Hopefully I do. Oh, there you go. You see a few things. Top right, that's the first-person view of what the robot sees. And then you have an overall view of what the robot is eventually doing. So as I said, in these videos, you have a lot of estimation, understanding, planning, and many other things that typically you need to have in order to solve this kind of task. This is the bull pushing task. Again, you see very low resolution, but enough for the robot to see the ball, locate the ball, go around the ball, and then push it in the right direction. We took this to another level by playing soccer, and we do the same. And that's very mesmerizing, so I'll just dive in directly into the videos because this is pretty good. Again, I'm not entering into the details, but it's first simulated, so that's the simulated environment, and then transferred into the real robot. There are a bunch of techniques nowadays to do that. They go under the name of sim-to-real transfer. Final result is pretty astonishing, so I want to show it to you. Again, same idea. Trained in simulation with very simple reward for just winning the game. That's the reward we give. We actually have a bunch of intermediate skills, we call them, like dribbling, kicking, and many other things. But this is real time. You don't get to see many real-time videos nowadays in robotics. Not specifically at Google DeepMind, we don't have many real-time videos, I have to say. I think Giacomo saw the video live, and you can trust, if you don't trust me, trust him, that it really works this way, and it's fun to watch. You can watch them endlessly and have continuous fun of saying, oh, look at that, look at this other thing. It's extremely entertaining. This video is on YouTube, and you can definitely have a look at it. Let me just stress on one thing at the beginning. There's an interesting strategy, which is just after this video here, this clip here, kicking the ball on the corner in order to avoid the opponent. So kick the ball in the corner, get it back, and then kick on the goal. I think that's kind of interesting. Remember what I said at the beginning? There's an important component about generalizing with language, and that's what we're doing now. The soccer task is interesting because it's very dynamic, but there's nothing about what I told you before. So we want to instruct the robot in a more natural way. The way to do it is through using large language models in conjunction with actions, and that's what I will just go through briefly. In particular, one approach that we did is called RT2. It's a little bit of a busy slide, but what you can get from this slide is on the left-hand side. We basically took one of these language models you play with, ChatGPT, and we added a few tasks. So you see a few tasks on the top left are the natural one, question and answering, like what is happening in this image, and then a great donkey walks down the street. Then there's French, there's a bunch of language tasks themselves. And then what we did is adding a bunch of similar data, but in this case, the data contain movements of what the robot is supposed to do. So in a sense, you couple language knowledge together with grounding into what it means to do certain actions. And you see it on the bottom left. What should the robot do to, and then it's parametric on the kind of task, to fetch the crisps from the drawer. And then you have the answer is actually an action that you feed to the robot. And then you basically do this approach and see if there is any transfer from the language capabilities to the motor capabilities. And that's what we observed. I will just go briefly through these numbers, but what you see in particular on the right-hand side of this slide is that we can perform unseen tasks and generalize actions that have been seen in a particular context into new contexts. And then I will conclude with one paper that we published before actually merging with Google DeepMind. It's similar in essence to what we have seen and presented just before. It's extremely focused on robotics and has particular type of assumptions. One important bit is that, again, we need to provide demonstrations of the tasks we want to solve. In this case, there are a bunch of assembly tasks. You see the gear assemblies. They are collected by asking people to solve the task through teleoperation. What we do is, represented in this slide, is we keep iterating this process. So we start with collecting some data. We try to solve a certain number of tasks, possibly new tasks. We collect new data by letting the agent try to solve new tasks. We filter them, seeing which one of these processes is successful, and then we spin the wheel, as we say. So we keep feeding the data created by the robot to fine-tune and improve the performances in new tasks that were not initially demonstrated by the teleoperators. And we did this at scale. So you see there's a variety of tasks happening here in a relatively simple environment where you have a parallel gripper, so it's a claw gripper with two fingers grasping an object in a small contained basket. But you see a bunch of objects that can be used from simple blocks like the one kids play with to gear assembly, as we call them. This is inspired by a benchmark proposed by the National Institute of Tunnel Technologies, and even to simple grasp actions on natural-looking objects like vegetables. And we also do this with different type of arms. That's, again, we bring in the generality. So we're not just focusing on one robot only, but we try to do many different, what we call embodiments. And that's another task. It's what we call shape matching, anyway, no big deal. So what we did was to massively collect a bunch of examples of tasks and demonstrations with these arms that were in the previous slide. So the one on the bottom here, simulated and non-simulated. It's a relatively massive data collection. And then we attempted to solve new tasks Not only new tasks like the one on the left, where you are, for example, putting vegetables into a cup, or you're trying to match shapes into a game, a kid game, but also we try to use very different embodiments. The one on the right-hand side is a new hand, multi-finger hand with a lot of dexterity similar to the human hand. Completely new. It was not in the data we used for training the first agent, so it's what we call a held-out embodiment. And we asked to solve the similar tasks, and long story short, we got a good success in that sense. I think it's in the right-hand side, so probably, yeah, there you go. With just 1,000 demonstrations of the new task, we could fine-tune and specialize this, what we call generalists, so a network that can do many things, to the new task. And I think, yeah, I have a small video that we'll skip because it's online, and I think I can go to the conclusions. Yeah. Well, I think that I was trying to sort of describe how I think that deep neural networks can represent complex control actions, that these controllers can be learned on real systems. Learning of this system requires additional information. We either use accurate simulations or first-person demonstrations of the task, or multi-agent learning, as we have seen in soccer. I think there's a hope that large neural networks can really represent large amount of behaviors, not just language, but also including actions. Yeah, and that concludes my talk.